Transistors are made of semiconductor materials such as silicon. Silicon is a quadrivalent element. Consequently, a silicon atom has 4 electrons in its outermost shell, which are called valence electrons. Each valence electron of a silicon atom wants to connect with another valence electron of another silicon atom. This will happen to all valence electrons, and they will form eventually strong bonds with no free electrons available to provide an electric current. Impurity atoms are incorporated into the material to increase conductivity. This procedure is called doping. Doping is, for example, possible with pentavalent elements such as phosphorus, but it can also be realized when trivalent elements such as boron are used. When different doped layers are placed in contact with each other, the basic structure of a transistor is born. One layer is doped with phosphorus atoms, which provide extra electrons. These electrons are free. The other layer is doped with boron atoms, which have only 3 valence electrons. That way, holes are created. A free electron of the n-type layer is recombining with the hole of the p-type layer, resulting in a hole in the n-type layer. This will happen to other electrons. This diffusion process creates negatively and positively charged atoms that are called ions. The electric field created by these ions opposes the diffusion process for electrons into the other layer. Now, let's see what the structure of a transistor looks like. A transistor is made up of 3 layers of a semiconductor material which have been doped differently. An NPN transistor consists of a layer of p-doped semiconductor material sandwiched between 2 n-doped layers. The n-doped layers contain free electrons. They are called collector and emitter. The base is very thin and it contains holes that are also called defect electrons. The blue layers represent the electric fields that oppose the diffusion process of electrons as mentioned before. Under these conditions, the transistor acts as a barrier that prevents current from flowing, no matter how high the voltage between collector and emitter. However, if a voltage is applied between base and emitter that is high enough, electrons overcome the resistance of the electric field and move into the base layer. Recombination of electrons and holes occurs instantly in the base layer, but most electrons will not find a hole and are pulled towards the collector layer. Consequently, a flow of current between base and emitter as well as between collector and emitter takes place. The current will continue to flow for as long as the voltage between base and emitter is high enough. Let's have a look at a real-life example. This is a very simple circuit where the light is switched on and off dependent on the ambient light. The power source is a battery. The transistor is used as the switch. The resistance of the photoresistor decreases with increasing ambient light intensity. Furthermore, a light bulb has been installed that automatically lights up when it gets dark. Let's see this circuit from a bird's eye perspective. The current is split between the branches. As the resistor's resistance is very high, the base receives only a small current. Most of the current is flowing towards the collector-emitter junction, which is currently non-conductive. The photoresistor's resistance is low as long as ambient light falls on it. When ambient light decreases, the resistance of the photoresistor increases, which means that eventually the voltage rises to a level that allows a flow of current across the base emitter junction. The light bulb will light up because a high current is flowing right through the collector-emitter junction. That way, a low current through the base emitter junction will control a high current flowing through the collector-emitter junction without movement of mechanical parts.